let's state the so-called Helmholtz theorem. It says the following: if the curl of a vector function is equal to 0 in a simply connected domain, and the divergence of this vector function u is equal to 0 in infinity. This means just that the divergence of u approaches 0 when x or y approach infinity in absolute value. Then there exists a function phi such that the field u, the vector field, is equal to the gradient of this phi. So that's Helmholtz theorem. In this course we are going to assume that the vector field, the velocity field in the fluid, is rotational free, so the curl must be equal to 0. Moreover, we assume that this velocity field is incompressible. That means that the divergence of this vector field is equal to 0. So using this, and we know what the divergence is, we have that using Helmholtz theorem, assuming that the curl is 0, that is that the fluid is rotational free. Then we know that there exists such a u and a function phi such that the gradient of phi is equal to u. And the gradient is, as before, the partial derivative of this phi with respect to x and y in these two components. If we now take the divergence of this u, that is equivalently taking the divergence of the gradient, this gradient, we should get 0. This should be 0. So, well, we can take the derivative of the first component with respect to x plus the derivative of this component with respect to y. And what do we get then? Well, we get the Laplace equation. So this means that the function phi is an harmonic function. So in the same way as before, we can find the complex potential in this way, in this form, where the real part is this function phi, and the imaginary part is the harmonic conjugate of this function phi. We are going to use this in finding streamlines and solving fluid problems in some examples.